Hello everybody, my name is Kyle Champ and I'm going to be talking to you today about Akamai DNS, one of the world's largest authoritative DNS infrastructures. So first, let's talk about what authoritative DNS infrastructures are real quick. I'm going to use the example of an end user like you or me trying to visit some page in their browser on their laptop. The first thing you do, right, is you type in a URL into the URL line, and your computer is going to send a DNS query then to a recursive resolver to look up that host name and get an IP address to actually connect to, right? And that recursive resolver, assuming it doesn't have the answer in its cache already, is going to go out and query potentially multiple different authoritative DNS services in order to obtain an answer. And Akamai DNS is one of those authoritative DNS services. It's responsible for a portion of the DNS hierarchical tree of namespaces, right? So eventually the recursive resolver gets an answer and it returns an IP address to your computer, and then you're able to go fetch whatever content you ultimately really wanted to go see in the first place, right? Process done at that point. During its diurnal cycle at peak, on any given typical day, Akamai DNS is answering over 5 million queries per second. And these queries are for various different domains. First and foremost, they can be for the Akamai Content Delivery Network, or CDN, and for content that is served by the CDN. So if you're trying to fetch something from a particular website that happens to be operated by some enterprises that choose to use Akamai as their content delivery service, then you will end up going through the CDN for that, and you'll go through Akamai DNS first. Also, various enterprises simply use Akamai DNS for the DNS part of their services, and these applications that they're running run the range of applications that you can find on the internet. But again, Akamai DNS prefaces all of these services, right? So in aggregate, Akamai DNS is answering billions of queries every day, and it's the starting point for a significant fraction of the world's internet interactions, right? That, of course, means that Akamai DNS has a critical role in the internet ecosystem, right? Because if Akamai DNS is not available, then the services that depend upon it are very likely not available as well. As such, resiliency to both any sort of failure or any sort of attack is paramount to Akamai DNS, and it's built into the design of the infrastructure. So let's talk a little bit about that infrastructure then, and let's blow up this cloud that is Akamai DNS. And first, we're going to look at it in terms of our deployment. The name servers that answer DNS queries that Akamai DNS receives are distributed around the world in points of presence, or POPs. And these POPs are in over 157 different countries. Each one of these POPs houses, of course, multiple different name servers. And to load balance DNS traffic among these POPs, we use IP anycast. That's, of course, the notion of advertising the same IP address prefix or space from multiple different physical locations, POPs in this case, right? So, for example, these POPs here that you see on the slide, they might be all advertising the same anycast prefix, right? And then a recursive resolver, for example, this one here in India, will then get routed to any one of these POPs if it tries to query Akamai DNS. In this case, it's going to be routed to, I believe that's Singapore. And that's a reasonable approximation of a highly performant and a reasonable load balancing result as well for Akamai DNS to spread the load across our POPs. Let's zoom in then and look at one POP in detail and look at its infrastructure. In general, at the highest level, a POP involves a router and then multiple machines in racks behind that router. I'm just showing two here on the slide, two machines, but in practice there of course be many more. It's just easier to explain this way, right? And each one of these machines runs multiple different services. First, of course, there is the authoritative name server that receives DNS queries and then answers those DNS queries. And alongside that is a BGP speaker. These are actually the origins of our anycast prefix advertisements, right? So these BGP speakers advertise to the router our anycast prefixes. There's a monitoring agent, however, that tells the BGP speakers whether or not they should advertise. And it does that based upon whether or not the name server is healthy. And we'll come back to that concept in a moment. But let's assume the name server is healthy right now and the BGP speaker is advertising. The router then receives these advertisements from all of the BGP speakers within the POP and then advertises on to its peers, whatever these routes are, right? And the number of peers for any given POP can vary dramatically. Some POPs may only have one peer if they are, for example, dedicated to a very important, very large ISP such as BT or Deutsche Telekom or something like that, right? But other POPs can have on the order of several hundred peers if they are connected to an IXP. Regardless, the infrastructure is the same. The router advertises these prefixes to its peers, and then the peers, using BGP policies and best practices, advertise these prefixes on to the rest of the internet. Ultimately, though, the result of this is that some amount of DNS traffic then arrives at this POP, gets routed to the POP, right? When the router receives this traffic, it uses ECMP, or equal cost multipath, to spread the traffic among the machines within the POP. And this results in a roughly uniform distribution of traffic, DNS traffic to be precise, among the machines within the region. So each machine can expect to get an equal percentage. In this case, it would be 50-50 between the two machines. Okay, so that's a very high-level picture of our architecture. Let's talk about something more interesting then. Let's talk about the resiliency that this architecture gives us, right? And we're going to talk about this in terms of first failure resiliency, and then we'll talk about attack resiliency. With any large distributed system like Akamai DNS, there are, of course, many sources of failure. In fact, at any given time, there might be multiple failures ongoing, right, with various different components. And Akamai DNS is architected to be resilient to all of these sources of failure. I'm going to talk about just a couple here. There's more details in the paper, and I encourage you to go check them out. The first one I'm going to talk about is what happens if Akamai DNS just starts returning an incorrect response. Let's say there's a name server, right? And for whatever reason, there could be many different reasons why this happens. It starts returning responses that are incorrect to recursive resolvers. We deal with this with a fairly general mitigation strategy, and I'm going to walk through this step by step. First, our monitoring agent detects the issue. For the case of incorrect responses, it may simply observe that the responses returning from the name server are not what it expects the name server to be returning, right? It also might be running active tests itself against the name server and observe that the responses it gets to its own queries are incorrect. But regardless of the mechanism, the name server has detected, the monitoring agent has detected an issue. At that point, the monitoring agent instructs the BGP speaker to withdraw the BGP advertisements. Okay? So before this, the router was receiving an advertisement from the two machines. After it, the router is only receiving an advertisement from the bottom machine. And as a result, all of the DNS traffic shifts, and all of it, instead of just 50%, starts going to the bottom machine, right? So effectively, the first machine has now been taken out of service due to the detected issue. What if, though, the second machine detects an issue as well? So again, its BGP speaker withdraws its BGP advertisement, and now the router has no advertisement. So it withdraws the advertisements from its peers as well. And now the entire POP is effectively out of service. This failover between machines within a POP is nearly instantaneous. Failover among POPs, however, since the traffic will be routed via Anycast to another POP, is dependent upon BGP propagation, right? The withdrawal of the advertisements from this POP needs to propagate far enough that the advertisements from other POPs gain precedence over it, right? In practice, we find that this failover is quite rapid, typically less than 1 second. And we have some measurements and methodology that we share in the paper that goes into this in some detail. Please take a look. All right, so that's how we would mitigate DNS name servers responding with an incorrect answer. Let's talk about another potential source of failure. The name servers, of course, require some inputs in order to answer DNS queries, right? This may be in the form of zone files, particularly for enterprise zones they choose to host on Akamai DNS. But it can also be in the form of our Akamai mapping intelligence, which tells us how to map into users to the HTTP proxies that make up the edge of the CDN, right? All of this data the name servers need to consume in order to respond correctly to DNS queries. there's a constant flow of a large amount of data coming into these name servers that they need to have. However, there is always a risk with every single new input that we receive that something might go wrong. There might be an unknown bug that causes the name servers to crash, perhaps because an input is corrupted in a certain specific way. And upon receiving this new input, the name server crashes. Note that our previous general mitigation strategy that I mentioned here won't be effective here, right? Because if the name server crashes and we withdraw our BGP advertisements, we've effectively withdrawn our BGP advertisements everywhere since all the name servers receive the input, and we've now effectively stopped answering DNS queries. Akamai DNS is not available, and that's not tolerable. So we have a special mitigation strategy for this particular type of very serious but highly unlikely failure, right? And that's with special name servers. So the bottom name machine here is colored slightly differently, and that's to indicate that it's special. It's what we call an input delayed name server. And as the name might suggest, the input delayed name servers receive inputs with an artificially imposed delay, right? Now you notice also on the graphic here that it's currently not receiving any DNS traffic, and that's because these machines also advertise anycast prefixes to the router with a lower priority, so typically they are not preferred by the router. But if the top machine receives a new input and the name server crashes, then the monitoring agent is going to withdraw the BGP advertisement, right? At this point, the router now only has one advertisement, the lower priority, from the lower priority advertisement from the bottom machine, and all traffic starts flowing to that machine. Of course, if this should ever happen, and it happens extremely rarely, I should note, Akamai engineers, Akamai ops folks are going to be on the bridge, all trying to discover exactly what the issue is and get the system back up to full availability, right? But note, during this time period, Akamai DNS is still up. It's answering DNS queries. It's just answering them based upon slightly stale inputs. And this is an explicit design decision on our part, right? We believe that answers that are potentially stale, potentially old, is better than not answering at all. So we consider it basically a degraded mode rather than a total lack of availability, a total DOS of the Akamai DNS platform. Okay, so that's failure resiliency. Let's talk a bit about attack resiliency next. And when we're talking about attack resiliency here, we're really talking about distributed denial of service attacks. And the goal of these attacks, from the attacker's perspective, of course, is to prevent Akamai DNS, or any other authoritative DNS platform for that matter, from actually answering legitimate queries, right? This is not an attempt to gain control or gain access or elevated permissions or something like that. This is to DOS the services, effectively. And of course, remember, if Akamai DNS is not able to respond, then all the services on the internet that depend upon Akamai DNS are effectively down as well. So let's go back to our deployment for a second, because I need to provide a bit more detail on what's happening here. First, these are our POPs distributed around the globe, right? But we actually have multiple anycast prefixes, and I'm going to use the letters A through G color-coded to represent these anycast prefixes. And each anycast prefix is advertised from different POPs. So for example, A here is advertised from 4 different POPs, while B is advertised from 3, and so on and so forth, right? No POP advertises more than 2 of these anycast prefixes. What this means from a recursive resolver perspective is that there are choices here, right? To query Akamai DNS, our recursive resolver in India can query any one of these. And note, depending upon which anycast prefix it chooses to use, it gets routed to a different POP with different name servers, different capacity behind it, right? This has a couple of advantages, and I'm going to use 2 DNS zones hosted on Akamai DNS as an example here. So there's example1.com and example2.com. Example1.com is delegated to A through F, right? 6 different of these anycast prefixes. So you can query any one of those and you'll get an answer for example1.com. And example2.com is delegated to A through E plus G. So notice that their delegation sets are different by 1, right? Now, we already mentioned that recursive resolver can query any one of these delegations, right? And they'll go to a different POP. That means if someone launches an attack and tries to DOS example1.com. Effectively, if they are only able to prevent answers from being returned from 5 out of 6 of these pops, example1.com is still available, right? So they must actually DOS the full capacity of 6 different pops in order to take example1.com offline from the perspective of this single recursive resolver, right? Further, let's say for the worst case for example1.com, the attacker is successful and is actually able to prevent all 6 of these different pops from returning an answer for example1.com. In that case, example2.com is still resolvable from this recursive resolver because there is still the G delegation, right, that goes to a different pop, which is still available, still up, and still can answer DNS queries. This is an example of compartmentalization within the infrastructure, right? Even in an extreme scenario of such a large DDoS attack that the target, in this case example1.com, is completely unavailable, the Akamai platform compartmentalizes that attack and still can be available, still can be up, responding to queries for other domains. Okay. Next, for mitigating attacks, the name servers themselves have some built-in automated mitigations to prevent DDoS attacks from having a large impact. And one of those built-in automations is our prioritizing of legitimate queries over suspicious ones. And the name servers do this via a 2-step process. First is what we call query scoring. As each query arrives at the name server, it passes through multiple filters. And these filters then, each one of them, apply a penalty to the query based upon some features of that query that they find suspicious, right? Then the query is added to a queue according to whatever the total penalty across all of these filters is. And if the penalty grows large enough, we may simply drop it outright as no longer suspicious, but outright malicious. In the second step then, in the query processing step, these queues are actually read in order of increasing penalty. This has 2 effects. First, low penalty queries are preferred. We'll read those first and we'll try to answer them before we answer higher penalty queries. But also, high penalty queries may potentially be discarded because higher penalty queues can starve. If there are enough low penalty queries that consume or saturate the available capacity of machines, then the high penalty queues will never be read, and those will eventually just be discarded. Let's take a look then and see how this impacts production traffic in a testbed demonstration of filtering, right? So in this scenario, there is a name server, and we're sending a fixed rate of legitimate traffic at it, right? It's consistent over time. And then we're increasing the rate of attack traffic that we're sending at the same time. So the x-axis here is the attack rate, and it's growing as we go to the right. And the y-axis is the percentage of legitimate queries that we're answering, right? It starts off, without filtering of course, that we're answering 100% of legitimate queries. If the attack rate is low enough, we're able to answer everything and there's no problem. However, eventually when we reach this point, the name server is now saturated. It's answering every single query it can, and it's still falling behind the line rate of DNS queries that are arriving at the name server, right? And at this point, the application starts dropping legitimate and attack queries at an equal rate because it's not filtering. Let's see what happens when we turn on the filter. You can see with the filter, past that point, we continue to answer 100% of legitimate queries. And this is because we're prioritizing them over the attack queries. Queries are still being dropped, it's just that the queries being dropped are attack queries at this point, right? Eventually we reach this point, however, where we start dropping legitimate queries as well. And this is the I/O capacity of the name server. At this point, the name server application itself is not able to keep up with reading off of the socket all of the DNS queries that it's receiving. So there are drops happening below the application layer in the kernel or even at the NIC potentially. But this shows the effectiveness of filtering, right? We're able to answer at a far higher aggregate rate of DNS queries. We're able to answer still 100% of the legitimate traffic that we were receiving based upon this filtering. Now there are many different filters, and we talk about them, most of them, in detail in the paper. So I encourage you to please read about them and discuss them. Now those are, of course, two aspects of how the architecture is designed to be resilient against attack, of course. But in the worst case, we still recognize that there is the possibility of an attack that is indistinguishable from legitimate traffic, right? In that case, filtering will not be effective, right? So Akamai DNS, as I've said repeatedly at this point, must always be available. And we build in contingencies for even extremely unlikely but high impact scenarios. And we do this in three ways. We over-provision bandwidth and peering links. We over-provision the compute in the name servers, and we compartmentalize the infrastructure to minimize collateral damage, as I mentioned before. So in conclusion, I've presented some of the design principles and the insights that we've gleaned from operating Akamai DNS for over 2 decades, and shown how the architecture provides failure resiliency and attack resiliency. There are many more details. Please check out our paper for the rest. Thanks very much.